Let's explore a fundamental property of exponents that's crucial in algebra. When k raised to the power of n equals k raised to the power of m, we can conclude that n equals m. This property only holds under specific conditions when k is greater than 0 and k is not equal to 1. These restrictions are important because the property breaks down otherwise. To understand this concept better, let's examine a concrete example using the base 2, which meets our conditions of being positive and not equal to 1. On the left, we know that 2 cubed equals 8. On the right, we have 2 raised to some unknown power x, which also equals 8. By our exponent property, since the bases are the same and the results are equal, the exponents must be equal. Therefore, x must equal 3. Let's visualize this relationship on a graph to see why only x equals 3 can satisfy our equation. This graphical representation will help us understand the uniqueness of the solution. The blue curve represents the exponential function y equals 2 to the power of x. Notice how this function increases rapidly as x increases, which is characteristic of exponential growth. The horizontal red line represents y equals 8, which is the value we're trying to achieve in our equation 2 to the power of x equals 8. The key insight here is that the exponential curve and the horizontal line intersect at exactly one point, where x equals 3. This is because exponential functions with bases greater than 1 are strictly increasing. They never take the same value twice. This graph confirms our algebraic conclusion. The equation 2 to the power of x equals 8 has exactly one solution, which is x equals 3. This is a direct visual demonstration of our exponent property. This uniqueness of solution is not just specific to base 2, but applies to any positive base except 1. When k is positive and not equal to 1, the function k to the power of x is either strictly increasing or strictly decreasing, which means it maps each input to a unique output. For bases between 0 and 1, the exponential function is strictly decreasing, while for bases greater than 1, like in our example with base 2, the function is strictly increasing. Both cases ensure that if k to the power of n equals k to the power of m, then n must equal m. To solidify our understanding, remember that for any positive base k that's not equal to 1, if k raised to the power of n equals k raised to the power of m, then n must equal m. This one-to-one relationship is what makes exponential functions so useful in many mathematical contexts. Let's explore the properties of exponential functions in the form f of x equals